Okay, so we'll today start doing curve sketching and the effect of derivatives on the shape of the graph. So let's say curve sketching. Okay, let's review the things that we did so far. Okay, so we want to sketch the graph of, say, y equals f of x, okay, on some interval, say I can be all of R, which is in general the most interesting case, or an interval, or subinterval. Okay, so it can be lots of things. Okay, so it can contain infinity. It can be a closed bounded interval, etc. Okay, so we'll refer to it as I. So we expect generally we'll be looking at f. F is differentiable on I, okay, except maybe at a few points. Except maybe at a few points. Okay, so we want to we make this assumption because most of our important functions are differentiable. Okay. So what we want to see in this graph is the following. In the graph. So most of all, we are interested in local minima and local maxima. And global min max, if they exist. Okay. And how fast the function is increasing or decreasing. Okay, so that increasing or decreasing has to do with this, the derivative. So derivative gives us information about this. Okay, the speed of the derivative is now the second derivative. And this shows itself as concavity. Okay, if the speed is increasing, so if this is accelerating, so the graph tends to go up faster and faster, so it makes it concave up. Okay, so we read this geometric property as saying that the speed is increasing. And in most cases, we are also interested in the extreme cases. Okay, when you are doing science, that's one of the main questions: what happens in the extreme? So that's the endpoints here. So also we want to know how the function behaves. How the function behaves at the endpoints of the interval. Sometimes it's easy to decide because you just evaluate the function at the endpoint. Sometimes the function is not defined at the endpoint, so you have to take one-sided limits and see what the function wants to do when it approaches to the endpoint. And if the interval is infinite, you take the limit as x goes to plus infinite or minus infinite. Okay, so these are the information that we want to put on paper so that when we stare at the graph, we immediately read this information. Okay, so starting from here, the easiest part, well, theoretically the easiest part is the first one. You take the derivative. Okay, so local mean max appears at critical points or endpoints. Okay, so critical points are points where either f prime is 0 or f prime does not exist. Okay, so that takes care of technically what we want to do there. And the second derivative, the sign of the second derivative determines the concavity. So concavity is decided by the sign of the second derivative. Okay, so if f prime is positive, f double prime. Okay, so I'll write that later. So what's the other thing? Okay, so for the endpoints, for the behavior at endpoints, if f is defined there, we just evaluate f there. Otherwise, if it is not defined there, otherwise we take limits. Okay, so that information is also important. You see, sometimes we already do it here. Okay, because we are trying to find the minima maxima if the function is in a tendency of increasing beyond bound as it approaches the endpoint, then our local maxima is not going to be a global minima. Okay, so to tell the difference, we need this information. Okay, so for this thing, we have the first derivative test. Okay, so first derivative test. So basically, we said that if f prime x is positive for some x, okay, so for x in some interval a b, then f is increasing on a b. Okay, so if this is negative, f prime x is negative on some interval, then it is decreasing. Okay. Second derivative test. So if the second derivative is positive for x in some interval, then f is concave up on that interval. And if f prime is negative, then this is concave down on that interval. Okay, so I think these are the tests we did. Okay, so we did some serious examples. Today we'll do more. So main examples are x to the power n. Okay, so main examples for concavity. Here we need to add one more thing maybe. Okay, so in the graph, if f prime, if double prime changes sign at a point, then that point is an inflection point. It's called an inflection point. Okay, so this is again something that useful in drawing the graph, because concavity changes. You want to tie a concave down curve, for example, to a concave up curve. You want to know exactly where they touch each other. Okay, so for concavity, our f of x equals x squared or x cubed. The others more or less look like the same. Okay, so for x squared, we know that the graph is something like this. So this is y equals x squared. Okay, so this is my function. So f prime x is equal to 2x. You see here, f prime is negative. Here, f prime is positive, decreasing, increasing. And f double prime x is equal to 2, which is always positive. So that tells us that it's always concave up. And let us do this for this totally trivial example. This is exactly what we want to do for a general function, f prime and f double prime. Okay. So when x is minus infinite, x goes to plus infinite when you take the limit. When x is plus infinite, okay, and this is again plus infinite. So these, sometimes I write them there, sometimes you calculate it down. This is the behavior of this function at the endpoints. It goes up to infinity. The function is 0 here, okay, and the derivative is also 0 here, okay, and f prime is negative here, f prime is positive here, prime is positive here, positive here. So I said negative. It's negative here. Okay. So now we read this one. This says that the function is decreasing, and this says the function is increasing, and this says the function is concave up, concave up. Okay. So you put this information together to construct this part. In general, of course, our functions will be complicated, but the information we read will be here. So you also check if these things tie together. So for example, here, this one will be like this one will be like this, so they tie each other. They tie to each other. Okay, so this is what we do with the x squared. And x cubed is another example. Together with these two examples, we almost cover everything, because in other examples, in more complicated functions, pieces of the function will be like this. Okay, so another typical example is x cubed. F prime x is 3x squared. F double prime x is 6x. Okay, so we again do the same thing. So we have x, f of x, or I didn't write x there, so let me just write f prime, f double prime. Okay, when x goes to minus infinity, this becomes minus infinite. When x goes to plus infinite, this becomes plus infinite. and x is 0 at 0. F prime is also 0 here. F double prime is also 0 here. And F prime is always positive. F double prime is negative here, and it is positive here. So this says that the function is increasing. This says the function is increasing. This says the function is concave down. This says that the function is concave up. And here you see concavity changed. Okay? The second derivative is 0, and the concavity changed. Okay, so, and we all know the graph of x cubed. It's something like this. y equals x cubed. Okay, so you see at this point the concavity changed. This is an inflection point. Okay, so this is inflection point. So the function is always increasing. Okay. On the negative side, the speed of increase decreases. Okay, and when x is positive, it increases. The function is increasing, and the speed with which it is increasing is increasing. That we read from here. Okay, so these are typical examples. Now, if you look at x to the 4, x to the 4 will be something like this. X to the 5 will be something like this. And in other examples, we will see parts of the function looking like these things locally. Okay, so I think these are... So this reviews what we did. So now let's look at how we do this part for more complicated functions. Here it was obvious. Okay. So let us look at limits at infinity. Okay, so limits at infinity. Okay, so we want to understand the behavior of f as x goes to infinity. Technically, that's limit of f as x goes to infinity. Okay, so limit of f of x as x goes to, say, plus infinity. Okay, so suppose this limit exists and it is equal to some number. Okay, generally we denote limits by L. So let me write L. So what does it mean? Means that no matter how large a number m you think of, okay, so remember we play games, think of a number divided by 2, add 5, tell me the result and I'll tell you the number. So this is like this. You think of a huge number, okay, there is a point x sub 0, let's say, such that for all x larger than or equal to x sub 0, we have f of x is larger than or equal to the number you think of. No, I told you the limit is infinite. Okay, so this is, first of all, okay, let's do this. First of all, this is the limit. Okay, so limit of the function as x goes to infinite is infinite means this thing. The function is increasing. And similarly for putting minuses here or here. So you have to take care of in which direction you are going. Okay, so this is, now the interesting thing is what happens limit as x goes to infinity f of x equals L. Okay, so now here the idea of thinking of a large number is you are trying to think of a number close to infinity, and the function always passes that limit. Hey, here the limit is, the second limit is just everyday limit. Okay, and if the limit is finite, now neighborhood of that number, after a certain point, the function will be in that neighborhood. Okay, so first let's draw a picture. Okay, so we are going to infinity. So let's draw it like this. This is y-axis, and we are saying that the limit will be infinite. So you can think of an interval around here. Okay. We agree that limit operation is getting closer to something. You are not evaluating the function there. So the question is how close will satisfy you. So you say you choose a small number, let's say epsilon. We traditionally use epsilon to satisfy everybody's needs. No matter how small an epsilon you choose, there is this band around here, and the graph of the function will eventually lie there. Okay, so the graph of the function can be something like this. Okay, but then after a while it will be here, and then from here on it will always be there. Okay, so from this picture we see that from this point on, the graph is inside the epsilon band around L. Okay. Now clearly this point depends on epsilon. Depends on epsilon. If you choose a larger epsilon here, you see that if you choose something like this, then I will say so from this point on everybody is here. If you choose a smaller epsilon, then this will not work. Okay, maybe I have to go further away. But the thing that we want to observe is that no matter which epsilon we choose here, we are able to say this sentence. At some point we will put our finger and we will say that from this point on the graph lies inside this band. If the function is satisfying that, if the function allows you to do that, no matter which epsilon you choose, then this is how we summarize it. Okay? So everything we said here, that whole paragraph, is summarized by saying that limit of f of x as x goes to infinity is L. Okay? Now, let's see what the picture looks like. Here, just to illustrate the point of the limit, I did not draw this line. So let us draw that line and see what happens. Okay. Remember that we are reviewing this with the eye on sketching the graph of the function. Okay. So if limit of f of x as x goes to infinity is equal to L, then the graph approaches the line y equals L. Okay, so we know that, that's what it means. But now we are translating this algebraic statement slightly into geometry. So typically we expect things to be like this. Okay, so this is again a typical situation. Suppose this is L now. So this point is L. And we expect that, for example, this is typical, so it becomes like this. So you see it is asymptotically approaching to the line. So we call this line horizontal asymptote. Okay, for the curve y equals f of x, this line is called a horizontal asymptote. Okay. So let me see, is it time to talk about slant asymptotes? So I think I'll come to that Okay, we'll come to that later. So let us at this point try to calculate these horizontal asymptotes. For simple functions, we can guess what the limit will be, and then you calculate, you play with algebraic equations to show that what you guessed is correct. Okay, so I keep repeating this. This is always how you do science or mathematics. Okay, first you must have an idea. First you must say, okay, the answer will be this, and you walk towards that. Okay, but of course you don't insist that that will be the answer. Along the way you learn if your guess is correct or not. As you learn, you modify your guesses, but you should always know where you are going. There are certain exceptions, of course, but exceptions, generally we call exceptions luck. Okay, let's not go into philosophy of science. Okay, let's talk about, let's now do some calculations, calculating limits of functions. And then we do some examples from the book. Okay, so here is an example. Okay, so some horizontal asymptotes, or algebraically some limits at infinity. Okay, so 1. So my function here, this is called an easy example here. Let's look at how easy it is. This is x over square root of x squared plus 1. Okay, so what we learned in high school about limits at infinity is the first thing that we try. You divide numerator and denominator by highest power of x, and every time you have 1 over x or 1 over x squared, that goes to 0. You eliminate those things, and if you are lucky, a number remains, and that's the limit. Okay, so here what makes this almost interesting is we have a square root here. Okay, but what do we expect? Now, this goes to infinity as x. This is square root of x squared plus something. But when x is very, very large, those plus somethings don't count. So this is again square root of x squared. So this also goes to infinity like x. So we are dividing x by x. We expect 1. Okay, so that's our expectation. So let's check if that is true. Now that I have this, I had this in ad hoc calculation in my head, I start doing formal correct calculation to suit what I had in my mind. I'm trying to see these two things as the same power of x. So I can square this and take a square root also. Okay, so this is where I calculate. So let me do this with the different colors so that we know now I started to think about this. This is square root of x squared, and this is square root of x squared plus 1. Now here I'm taking a positive root because I'll calculate. Okay, so the question here was this thing. Limit as x goes to infinity of f of x is what? If we can also do this, limit as x goes to minus infinity of f of x is what? So here there is a choice. This goes to plus infinity. This goes to minus infinity. Okay. So the sign here will be according to this. You see, I'm saying that this is equal to this. If x is always positive, this is always positive, clearly. So here I have to take the positive square root so that they will be equal. Okay. If x is going to minus infinity, eventually this is going to be minus. So when I square and take the square root, and if I take the positive square root, then I'm not calculating the thing I started to calculate. So then it will be minus. Okay. So the sign is the same as the sine of x. Okay. So let's continue with this. This is equal to, oh no, I don't want to write this because last night I read hundreds of papers with this stupid notation. So I'll continue from here. So this part, let's put it in a box. Okay. So this thing, now plus or minus, I put everything inside square root x squared over x squared plus 1. Okay, so now calculating the limit looks totally trivial. I'll put now limit as x goes to infinity in front of all these things. There is limit as x goes to infinity here. That's why we studied continuous functions, at least the concept. If you have a continuous function, the limit goes inside. Square root is a continuous function. Okay, so look at the graph of that. It's not broken. Okay, so limit goes inside, and I'm trying to find the limit of this as x goes to infinity. Now, that's totally trivial. Okay, the limit is 1. I'm taking the square root of 1. I'll get plus or minus 1, and it will depend on the sign of x. Okay, so that is how I calculate this. Okay, so limit as x goes to, let's first do the plus 1. F of x is equal to limit as x goes to infinity. I'm here now. I'll take plus. So this is x squared over x squared plus 1. Now from continuity, this everything is under square root. Limit x goes to plus infinity of x squared plus 1. Okay, so I won't say anything here. This limit is 1, so this is square root 1, and that is 1. Of course, I can jump from here to here, but I'm here reminding myself that I have to take a square root, so I have to decide on the sign. Okay, I once again verify that I'm taking the correct sign, and I get 1. Okay, so if I was doing this thing, let's do it quickly. Now we can go x goes to minus infinity of f of x. This is limit x goes to minus infinity. Now the function I'm trying to understand is this one. Okay, so this one. Square minus square root of x squared plus 1. Okay, so this is now minus square root limit x goes to infinity minus infinity x squared over x squared plus 1. This is equal to minus square root 1 equals minus 1. Okay, so algebraically I found these things. Before I show it to anyone, I check by myself if this makes sense. I'll look at this thing. Okay, so this is negative when x is negative. Okay, so on the negative side, the result must be negative. And here I agree that this is behaving like x, this is behaving like x. So the ratio is almost 1, okay, and it is minus 1. So that this one works. And the other one is, of course, more easy. Everything is positive, so this behaves like x, this behaves like x. So the limit, I expect 1. Okay, so this second argument, I'm just using what I know. I'm not trying to be precise. This is just my checking. So my expectation from here and my algebraic results are the same. So now I can show it to others. Okay, this is a simple example which helped me to illustrate the in-between steps. In complicated problems, we'll use exactly the same in-between steps, but the calculations will be more important. So we will be tempted to forget the important steps. Okay, you should follow the rules, but if the problem is complicated, the calculations are, of course, more interesting. Okay, so sometimes there are tricky examples. Let's look at this one, for example, to limit x goes to infinity of sine x. Okay, so what do you expect for this one? So if somebody claims that the limit is 5, will you believe that? No? Well, if somebody says the limit is 0, will you believe that?
Maybe. It must be between the -1 and +1.
Yes, it must be between -1 and +1. Okay, so we are a step closer to the answer. And where do you expect this? Do you have an idea? Yeah, it is like that. So it is like that. Now you solve the problem for yourself. Now convince others without your finger, because they are not looking at your finger. Okay, your solution is correct. That's how we find the solution by ourselves. It is like that, so there is no limit. Okay, but now you have to write this to someone you have to explain this to Trump. Use a little bit more technical terminology so that everyone will agree. Like that translates to saying that the function is periodic, right? So the function is periodic, so it always comes back to the same value. Okay? So there is no single value that it approaches, because whichever number you think between +1 and -1, the function comes back to that number infinitely many times. So this limit does not exist. Okay? So does not exist since the function is periodic and takes every value between -1 and +1 infinitely many times. Okay, so now putting these two ideas together, we wrote a technical sentence which everybody should agree. Everyone who passed calculus knows what we mean. Okay, so that's why we develop technical terminology. Okay, so remember, if the limit of this was equal to L, we would put a band around L, a small band around L, and from some point on, the graph will stay in there. But any point outside the band, if I take the band small enough, there will be points outside the band between -1 and +1. So the function always comes back to that number. So it always leaves the band. Okay, so so this is how we explain it to ourselves. This is how we realize that the limit does not exist, doing this, and then we write this. Okay, but how about this one now? Limit x goes to infinity sine x over x. If limit goes to 0, we know that this is 1. If x goes to 0, the limit is 1. So this is sometimes an exercise which you ask in quizzes, and half of the class writes 1. So what do you expect here the limit will be? 0, because again we borrow this idea, this function sine x is between +1 and -1, but you are multiplying it with 1 over x, and 1 over x goes to 0, so squeeze theorem says that this is 0. Okay? So, well, we can immediately write this as 0 since sine x over x is equal to 1 over x times, we are going to infinity, so 1 over x is positive sine x. Okay, because of this thing, so we have okay, sine x is larger than 0 in absolute value. So sine x over x, I look at here, and it is less than or equal to 1 over x. Since sine x can never be larger than 1. Okay, then here I take the limit of both sides as x goes to infinity. This is the constant function, so it remains the same. So this one is one of our basic results. This goes to 0 as x goes to infinity, and by squeeze theorem, this goes to 0. Okay, so last night I was reading this question 3. We use intermediate value theorem and mean value theorem. Okay, in part A, intermediate value theorem. In part B, you use mean value theorem. So you would be surprised how many different names you read there. Squeeze theorem, other theorems. Okay, so some people have this idea that if you calculus book is something that you cannot understand. So if you write something you cannot understand in the exam, it will be mathematics. Okay, so it's not. Unfortunately, it doesn't work like that. Okay, so squeeze theorem, I remembered it for a long time. Okay, so these are simple examples, but they again illustrate certain points. If you have a periodic function, okay, you don't worry much about that. It doesn't have a limit. And in these cases, you don't get yourself fooled by the tricky things we did when limit of sine x over x goes to 0. When x goes to 0, you keep in your mind that x is becoming large. Does it doing anything to sine x? No, it doesn't, but it does something to sine x when you divide it by x. Okay, so that's how you think about this in your mind. Okay, so here I have 2 more interesting problems. So let me do this one now here. So let's do these 2 examples and then we'll take a break. So I have this example and and there has to be some 1 somewhere. Here, this one. Okay, so let's say 4. Let's look at this limit as x goes to infinity of this expression, square root x squared plus 1 minus x. Okay, so this is of the form infinity minus infinity, so we don't know what is happening. So in these cases, the trick we have is to get rid of this addition and make it into a multiplication. Well, division is also multiplication. So we multiply it by its conjugate. Okay, so this is limit as x goes to infinity. I multiply this. Okay, so let me show this thing. Let us not be lazy. I multiply this by 1, but I choose 1 to be this thing plus x plus x. Okay. So that thing now is limit x goes to infinity. So this thing becomes x squared plus 1 minus x squared, right? Square of this minus square of this. And here I have x squared plus 1 plus x. So these things cancel. Okay. Then you take x out. Okay. So this is limit x goes to infinity. 1 over x times, this is 1. So I divide this by x, this is 1 plus 1 over x squared, right? And I divide this by x, 1. Okay? So this is product of 2 limits. Now that we are patiently writing everything, let me write it like that. X goes to infinite 1 over x times limit x goes to infinite of 1 over square root 1 plus 1 over x squared plus 1. Okay, so this limit is 0 and this limit is 1 over 2, right? Here, of course, I don't need to calculate this limit exactly because I'm going to multiply it by 0. But I have to make sure that this limit is a number. so that I multiply that number by 0 and get 0. If this limit is infinite, or if this limit does not exist, then 0 times something that doesn't exist doesn't give me any result. Okay, just for that purpose, I calculate that, easily see that this limit is 1 over 2, so the limit is 0. Okay, so here I want you to notice how patiently I wrote all of these things. Okay, so these things should be there. Okay, if you are reading a typical calculus problem in the exam, these things are missing. Okay, now in your mind, erase those green areas and look at what we are doing. You have hanging equations here and there, okay, and then somewhere you have 0. Okay, so you take your red marker, put a cross here, and write 0. Okay, so that's really what happens, because that's not the way. The idea now, this is no more a multiple choice exam. Life is not a multiple choice exam anymore. It's over. Okay, that was something stupid. Our generation could not find a solution for university entrance exam. I accept the blame, but now you have to come up with a better solution. But that doesn't go here. Okay, you don't write hanging pieces. You don't put arrows. If you mean equal, you write equal. If you are carrying the limit operation, you must write the limit operation. If you are lazy, start with this. Erase all the limits, okay? So you come up to here, and then you stop here. Then at the final step, you say limit of this is equal to limit of this, and write the answer, okay? So what the idea here is, because that is what you have in your mind, you should write what you have in here. When you are writing this without these limits, that's not something in your mind. You are actually saying that I'm now calculating the limit. Okay, let's do one last example, very similar to this, but in that example, we have x instead of 1 here. So let's see what happens. Okay, so you see, what do we expect? Suppose I have x here instead of 1. That will show up here, okay? Instead of 1, I'll have an x here. That x will cancel with this x, and I'll end up with this thing. The answer will be 1 over 2. That's what we expect. Let's quickly check if that works. We want to calculate limit x goes to infinity of x squared plus x minus x. Okay, now I don't want to write limit all the time because I don't have time. So what I do is this, x squared plus x minus x is equal to x squared plus x minus x. I multiply this by this one, x squared plus x minus x, x squared plus x minus x. Now this is, now I am here, x squared plus x minus x squared over x squared plus x minus x. These cancel. Now I divide everything by x here. So x comes out, and inside I have 1 plus 1 over x. I'm dividing this by x squared, just like I did here. Okay, and I have this is plus, and here I have plus 1. Okay, now these cancel because I will eventually go to infinite, so x will be away from 0. So this is 1 over 1 plus 1 over x plus 1. Okay, so now finally I write limit x goes to infinity of this expression, x minus x. This is equal to x goes to infinity. I managed to change it into this form, 1 over 1 plus 1 over x plus 1. Okay, now the limit is obvious because this is a continuous function. The limit goes everything inside. So eventually I take the limit of 1 over x, which is 0, and everything is there. So this is 1 over 2. And I check in my mind that I'm not going to take negative square root here because this is given as positive square root, x is going to infinite. Okay, so no problem. The answer is 1 over 2. Okay, so you either do it this way, showing us what you have in mind. At every step you are taking the limit and meanwhile simplifying the expression. Or you just start with the expression, you simplify it, and then use it in your limit expressions. Because this is what goes through your mind. Okay, if you don't put it in the paper, in math department, we haven't yet started reading your minds. Okay, so one day maybe we'll develop techniques to read your mind. We'll show your paper to the machine, and it says, even though he wrote minus 15, he means x squared. Then we say, okay, x squared is the correct answer. But now when you write minus 15, we treat it as minus 15. And if it's not the correct answer, you don't get any points. Okay, let's take a break and think about this.